Good afternoon, everyone. My name is Gosia Szepulska, and I'm the Southeast Branch Chair. Welcome you all to today's session on corrosion. The presentation is Beginner's Guide to Cathodic Protection by Ken Lax from Corrosion Consult UK Limited. I would like to introduce today's speaker, which is Ken Lax. So Ken Lax began his career in marine radio and electronics, and had his first contact with cathodic protection in 1967. After some years at the sea, he joined the British Antarctic Survey and spent the winters of 74 and 75 at Haley Bay Geophysics Research Station. The summer of 76 was spent working at Cambridge, and the winter of 77 was spent at Haley Bay. In 1980, he became involved full-time in cathodic protection, initially in the design and manufacture of the transformer rectifier power supplies and pipeline surveying instrumentation, and later as a cathodic protection engineer. Ken is a chartered engineer, a fellow of the Institution of Engineering and Technology, a fellow of the Institute of Corrosion, and an NACE corrosion specialist. He is an active member of French Corrosion Society and German Cathodic Protection Society, and he has been a member of the Guild for more than 20 years. Since 2003, Ken has officially represented the Guild as a technical expert in cathodic protection, stray currents, and coating standardization working group. He is a chairman and a conventor of the ISO working group that has produced the first standard on the effects of straight currents on the pipelines. Ken is the technical director of a Corrosion Consult UK Limited. So welcome you, Ken, to today's presentation. Now, before presentation start, just a couple of notes to you. If you've got any questions, please type them into the chat box, and Ken will answer them in the end of the presentation. Now, can you please all turn off your cameras and mute your microphones? Okay, thank you. Ken, over to you now.
Well, thank you very much, Gosia. Good afternoon, everybody. Welcome to this presentation by Pipeline Industries Guild on behalf of the Southeast Branch, of which Gosia is the chairperson. And for those of you who are not yet members of the Guild, I hope this will inspire you to become a member of the Guild, because corrosion is just a small part of what the Guild looks after with respect to pipelines. And if you are at all involved in pipelines, then the Guild is really the best place for you to be in terms of keeping up to date with things. And also it gives you the opportunity, should you wish, to participate in drafting standards or having some input to how the industry works. Now, let me just see why my slides are right. There will be plenty of time for questions at the end, but if you can send them any time via the chat box, and about halfway through, I'll just pause and give an opportunity to respond to the questions there, because we're going to be following through this in logical steps, and if you don't quite catch a step, it's useful to consolidate that understanding before we proceed. There's no doubt about it, cathodic protection is a complex subject, and it's outside the scope and remit or interest of many people in pipelines, but it's always a part of a project. And it's good to have an understanding of other disciplines involved in pipelines outside of your own. So as Gosia said, I've been a member of the PIG for a long time and represented them since 2003 on the CEN, which are the European standards, CENELEC are the European electrical standards, and the ISO standards, which are the international standards. The paper has been, presentation has been put together by Richard Lindley and myself, and also from the guild member, Dr. Thomas Löffler from Decotech. So it's a little bit different from a normal PowerPoint because they always tell you in PowerPoints, keep them short and slick and to the point and just hit the main points and then talk around them. But because this is being recorded by PIG and the PowerPoint presentation will actually be distributed to anybody who wants it, it'll be downloadable from the website. I've put a bit more blurb in than usual so that people will be able to just read it as a standalone document. And I hope you'll bear with me on that. So you should always start apparently by telling people what they're going to get out of their presentation. Well, I'm going to tell you what you won't get out of it first. You will get an understanding of what's involved, but you won't be able to design or specify a corrosion protection system. You won't be able to argue with the cathodic protection engineer on site, but at least you'll have a very, very good understanding of how it works. There's a lot of science behind cathodic protection and maths, but we won't be talking about that. There won't be any electrochemistry. There won't be any complicated formulas. I'm going to give you an understanding of what happens and what's needed to make it happen. But before we do that, there's interesting stuff. There's approximately 2.5 trillion US dollars, and that's just a shade over 2 trillion pounds sterling, the global annual cost of corrosion. And what's even more surprising is that 80% of that can be avoided by the use of existing technology and techniques. And that's rather shameful. So here's what we're going to describe. First, I'm going to tell you why the steel corrodes. Then I'm going to tell you something about the role of coatings, because you can't understand cathodic protection really unless you've got some concept of what coatings do. And then I'll describe the different types of cathodic protection. And then the last 2 points are something that's becoming more and more important, and that's the effect of unwanted DC current and AC current on the pipeline. Now, I was encouraged in this by a member of the Southeast branch, Mike, who's here today, and we agreed that perhaps the best thing was to assume absolutely no electrical or electrochemical knowledge in the audience. If you find some of the explanations a bit patronizing or oversimplified, because you do understand some electrical principles and electrochemistry, just bear with us, because there will be more than half, I would think, of the audience who don't have any electrical or electrochemical knowledge. If you want to go a little bit deeper, I've given some further guides towards the end of the presentation, but you can always contact me. My email address will be at the end of the presentation if you want to take it a little bit further and want to know a bit more about what's involved. So the first thing is, why do pipelines corrode anyway? Why can't they just sit where they are? Well, it's due to the universal laws of energy conservation. You can't create or destroy energy. It just moves around and changes its form. So you can see at the bottom of the little graph there, it's the natural state of the metal. It's just a crumbling ore. It doesn't want to be anything else, just wants to be left alone. A bit like a teenager in a bedroom, Catherine. Just wants to be left alone. But then we dig it up, which takes an awful lot of energy. We drag it to the surface, and then we move it to a big smelting place where we heat it to enormous temperatures and throw in a couple of other bits and pieces to the mix. And then eventually we get this bit of red hot molten steel coming out. And then we, if it's a pipeline, we then roll it and make it into a tube. The minute you leave that, it will start reverting back to being an ore. The process is quite slow in the absence of any external interference. But if you get acid rain, or if you bury it in corrosive soil, or if you apply currents to it, which we'll talk about a bit later, it will corrode rapidly. So we need to consider what a corrosion protection system is in its entirety. And really the work has to begin at the beginning of the project, where everything has to be specified carefully. It always comprises, well, it generally comprises a passive protection system, which is the coating, and an active protection system, which is the cathodic protection. Now, I know that there are some structures which are not coated, some of the older water pipes, some offshore structures, or I'd say the majority of offshore structures are not coated, but they're not what we're talking about today, really. We're talking about buried pipelines. So the first general mistake occurs in the specification of the coating. People don't pay enough attention to it. They just sort of tick a box on a bit of paper, and off the pipe goes, and it goes into some coating plant, and it squirts out the end, and then somebody drags it onto a truck, and the truck bounces along to the site, and then they throw it off on the side of the trench, and all the time the coating's getting damaged. And so when you're looking at specifying your coating, you need to look at the whole life cost, how it's stored and handled, how it's transported, how you lay down the pipe, what coating tests you do on it, how you repair the coating, how do you repair the field joints. That's where the pipe lengths are welded together. Obviously, if you're welding two bits of pipe together, you don't want any coating there, so they leave the end of the pipe bare or uncoated, then they weld it, and then they apply what they call a field joint coating, and that has to be compatible with the main pipe coating. And then you need to pay special attention where you've got a high risk of coating damage, such as rocky areas, pipe supports, where you're pulling the pipe through the soil, through a thrust bore, where you've got crossings and casings, all these sort of things. You need to take care of that. That's part of the system. And the coating is actually the primary corrosion protection, even though cathodic protection engineers like to think that cathodic protection is the primary corrosion protection. It's not, it's the coating. And for that reason, the coating has to be considered when you're considering cathodic protection, because it makes a huge difference to your cathodic protection design. And it's not just the condition of the coating at the beginning of the project, it's what state it's going to be in at the end of its design life, which may be 20 or 30 years typically. But I wish I had a penny for every time somebody had approached me and said, well, this pipe's been in the ground for 25 years, and what do we need to do to make it last for another 25 years? And that is going to be happening more and more in the present global economic climate. And that's when people are going to wish they put on a decent coating, because it might only cost you £1 to put a bit of coating on a pipe in a workshop. It's going to cost you £1,000 to go out there, get the way leaves, get the trucks there, get the diggers there, dig it up. When you get near the pipe, hand excavation, digging under the pipe, making enough room, repairing the pipe. It's a hugely expensive process to recoat pipes once they're in situ. So the surface preparation and application of the coatings has to be carefully thought out and needs to be supervised by specialists. And there are many, many standards for pipeline coatings for the different types and how they can be tested, how they can be applied. And not only that, how the surface of the steel has to be prepared for that coating, and also what qualifications people need in order to be able to do the surface preparation and the coating application. These are some photos of modern pipe coatings which are applied before the pipe goes in the ditch, and you can see the kind of tools and materials that are used and how easy it is to apply above ground. Imagine if you have to do that in a trench, not so easy. And what does cathodic protection do? Well, it complements or supplements the coatings to counteract where you've got corrosion taking place, where the coating isn't effective. And Places where the coating isn't effective are where it's been damaged and you've got a coating defect, often referred to as a holiday, or where the coating has absorbed so much moisture that it's practically transparent to electric current. And different coatings have different kinds of moisture uptake. So we're now going to get to the key technical stuff for cathodic protection. Now, corrosion is an electrochemical process, and you don't have to be a genius to realize that that means there are electrical and chemical elements to the process. Cathodic protection deals with the electrical side of it. The pedants will tell you that, of course, the electrical stuff only changes the electrochemistry, the chemical composition of what's happening. But for the purpose of understanding cathodic protection, it's just an electrical system. And electrical systems are pretty easy to understand, really. An electric current is just a flow of electrons. And we define it by saying how many electrons go past a point in a certain amount of time. And there's only one law that deals with direct current in terms of understanding electrical currents, voltages, and resistances. And that's Ohm's Law. And this is the only formula I'm going to show you today. And it's very, very important because the three features that we're interested in are voltage, resistance, and current. And they're interrelated. You can't separate them. And it's shown symbolically as I equals V over R. So you can think as the voltage as being the force that pushes the electrons around the circuit. And the resistance, whatever that happens to be, is what opposes that pushing force. And the current is what squeezes out of the resistance in terms of what we want to use for power. In this context, current equals power or energy. So if you consider that where you have electrons or current leaving a pipe in the soil, each of those electrons as it leaves, this isn't quite true technically, but it's perfectly acceptable to understand it. Each one of those little electrons takes a bit of metal with it. So the bigger the current, the more metal leaves. So you can see that if you increase the size of this value R, if that's a very big number and you're dividing it into that number, you'll get a smaller current. So if you've got a high resistance, you'll get less corrosion current leaving. And similarly, if you've got a very low voltage, you'll get less leaving. Now, this is the basic, very basic electrical circuit drawing. It could be for anything. The power source could be a battery. The load could be a lamp. Let's say it's a flashlight, for example. That could be a flashlight. And nothing happens until you close the switch. When you close the switch, you get a flow of current through the circuit. The circuit has to be complete for the current to flow through. If the switch is open, the current won't go anywhere. It doesn't go there and stop. It just doesn't go anywhere. So that is the basic circuit. And that is really important to understand, that it's nothing very complicated. If we look at a CP circuit, we can imagine that the ground level is here. That's a test post above ground, which you've probably seen along pipeline routes. Our anode is in the ground and our pipe is in the ground, and I've just shown a little coating defect here because the pipe has a high resistance coating, which we discussed earlier, and where it's damaged, there's no coating between the outside soil and the earth, or the electrolyte as we call it. It could be water or earth. And at this time, there's no current flowing because there's no connection here, just as the same as a flashlight. And if you look at the one down here, we've got our power source, which is the anode. Now there is a link in the test post to complete the circuit, so the current will flow through here, the whole circuit. So you've got the electrons trying to come out of here to cause corrosion, and we can force current back into it so it doesn't corrode. The ground or the soil is the return circuit. And the anode could be either a sacrificial anode or an impressed current anode. And I talk about those a little bit later on. But you can just think of it as a power source or an electron pump, really. So how does it do it? And this is the question that most people ask. It does it because it's just a very simple electrical circuit. When you make this connection here, the current can't help but flow. It's got no choice. It's not an option for an electron. Electrons are rather silly and feckless beings, really. It's a very interesting topic about how electrons and atoms behave. And it's something that we might one day do a presentation on, because it's such an interesting thing. But electrons just go where they're told. And we form in the ground what we call potential gradients, because this anode here has a certain voltage on it. It either comes from an external source, which we'll discuss later, or it naturally exists because the anode is a special type which sits at a higher voltage than this. If you put a piece of steel in the ground, we know roughly what its potential is, what its measurement or its energy levels are. And if you connect this one up with a higher energy level, if you plotted the lines of potential around, you'd see a slope going down from there to there, which means you can imagine it's a bit like if you take a ball onto the top of a hill or a slope and you let it go, it rolls down. And that's basically what the electrons do. They'll go down a voltage gradient. And here is an example of how cathodic protection actually works. Here we've got an electron pump, which is either an anode that's made from one of the galvanic materials or alloys, or it could be an impressed current anode where we've got extra power on it. And here we've got a coating defect. And it's got, don't worry about the units, it's got about 10 trying to leave the pipe, which would cause corrosion. But it stands to reason, if you can force more on than it's trying to come off, the net result will be some going on. So in this particular case, you've got 10 trying to come out, you've got 11 trying to go in, so you've got a net amount of 1 going in, just like a normal hydraulic forces, really. And that's the basis of cathodic protection. And if you grasp these circuit diagrams in this little image, you can collect your certificate as a CP expert. Now, there are 2 types of cathodic protection system. One is called galvanic, which is also sometimes called sacrificial, which I'll explain in a minute. And the other one is called impressed current. Now, the galvanic anodes have a driving voltage, which is the V in the Ohms law. And that driving voltage comes from the type of alloy it is. Depends what things we throw in the mix when we're refining it and melting it down and forming it into what we want. It's a bit like a battery. Well, in fact, the old-fashioned batteries, which the older ones amongst you will remember, where you had a copper rod inside some gooey paste, that was just a corrosion cell. And that's the voltage from that corrosion cell used to drive our torches. The modern batteries are a little bit more complicated. But nevertheless, that galvanic anode has a driving voltage between 1 volt and 1.5 volts, depending on what it is. And you can see from that if the resistance path was very, very high, because if you remember that the current is the voltage divided by the resistance. So if the resistance is very, very high, there might not be enough voltage to drive enough current through. So that's why we have to sometimes supplement these anodes or install a lot of them close to the pipe. The advantage of them is that they don't require any external power to operate. There are other disadvantages. There are disadvantages rather, and other reasons why we might not use them is that not just that they've got a limited power in distributing the current, but also they're a bit like an ice lolly, really. You never get to use 100% of them. After you use about 80% of them, some of them, they just tend to drop off the lollipop stick and the anode packs up. So you never get 100% out of them. And the impress current, on the other hand, those anodes don't have any natural energy in them to speak of. And we have to apply an external power to it, a DC power source, like a battery sometimes we use just to prove a point. And you might use what we call a transformer rectifier, which is just a widget that takes the mains power, your AC power, converts it to DC, and allows you to control the DC till you get just as much as you need. I think the greatest benefit of the impress current ones is the anode ground beds, as we call them. They last a lot longer. They can be adjustable. They can be provided with a power supply which automatically changes its potential in order to maintain certain levels that you give it, as kind of a feedback loop in it. So those are the two types, the galvanic and the sacrificial. Right, now I'll just take a little pause to see if anybody's put any questions in on the chat. I haven't been looking at the chat, Rosia. Have you been looking at it? Are there any questions yet? No.
No, I cannot see any questions yet.
Okay, that's good. Excellent. Right, we'll move on then. Now, on the next slide, I'm going to show you what we call the Galvanic Series. It just, there's a list of the stored energy values in these different alloys and materials. And if I just quickly slip forward, you can see here that magnesium is the top, aluminium is the next, and zinc is the next. Now, don't worry about these actual values against what they're measured against. I've deliberately not put the units in. I just want you to look at the rising scale. So if you connect magnesium to iron, then the magnesium will corrode in order to protect the iron. And similarly, if you can connect aluminium to iron or zinc to iron. However, if you connect copper to, let's find something reasonable. If you connect steel to copper, you see that the actual steel will act as an anode and will corrode away. Now, I mentioned earlier about the electrical gradient. That's really very important to understand this concept, especially when we come to stray currents and interference. But it's invisible, but it's, to an electron, it's just like seeing the top of a mountain and a valley. If it's at the top of the mountain, it has to get to the valley. It's got no option. And on the way, it'll do all kinds of strange things. But as I mentioned, we can talk about that a bit later. But it's, I suppose everybody's got the mental image that we all got from school about atoms and electrons being a bit like some kind of solar system with planets circulating around it. It isn't actually like that. It's not like some galaxy. The sizes and the distances are incredible. If you take a typical atom and you imagine that about the size of an apple. If you imagine an atom is about the size of an apple. If you now consider the electron and you consider the whole world, our world, the Earth, the apple with respect to the Earth is about the same ratio as an electron to an atom. There's that big a difference. It's huge. And the distance between them is enormous, absolutely enormous, by the size of an electron. So that's why we get such strange things happening, for example, on poor coatings, poorly chemically constructed coatings, because they leave such big gaps in them that it's easy for the electrons to leave. And that's something that comes up in when you look at these things in detail. So I think the moral you can get from this Galvanic series is that if you build your pipes of gold, you won't get any corrosion. Probably won't be much of your pipe left either, because it'll all be stolen. Now, impressed current anodes don't have a higher stored energy than the pipe steel. And in order to get the electrons to flow, we stick some power on it. You can use solar power, you can use power from wind turbines, you can use transformer rectifiers, you can use batteries if you're stuck. And although theoretically you could use scrap steel, in fact I have on some projects in the Soviet Union and the former Soviet Union, they instructed us to use scrap steel as ground beds because they had a lot of scrap pipe. They didn't want to buy any anodes, so we had to make the ground beds from scrap steel. Well, we needed a lot of steel because steel, you can force it to give up the electrons, but you lose the metal as well. So they get consumed very quickly and the cables fall off and so on and so forth. So we tend to use special mixed metal oxides or silicon ion anodes or conductive polymers. Those are just very generic. There are many variations within that, but all of them require an external power source and they all have a low consumption rate. So now we come to the CP design aspect. As I mentioned before, you can't separate coatings from cathodic protection. The quality of the coating and the performance of the coating has a massive impact on the CP design. And in order to do this design properly, you need to know about the coating quality up to the end of pipe design life. And the greatest amount of coating damage occurs during installation. Transportation and installation is where most of the damage occurs. And some people are smart enough to put in inspectors in the coating shops and also do what they call holiday detection on the coating before it goes in the ditch. And then they just say, oh, repair it. Well, of course, that's it's a license to the contractor just to do the minimum of repairs with the minimum of tests. The coating repairs need to be as heavily specified as the original application of coating. We need to know the total surface area so we can see how much current we're going to need to protect it. We need to know about the soil resistivity because that affects the passage of electrons to and from the pipe. We need to know how long you want it to work for. We need to know if there's any electrical interference, either from direct current or AC interference. You need to know if there's anybody nearby with a pipe or an earthing system. You need to know where the road crossings are, the river crossings, and the rail crossings, all these kind of things. Now, the difficulty is knowing where to put the anodes. I can tell you from experience, it's not where the project manager tells you we wish you to put them. Because it's quite an art. And one of the things I found useful to explain to people about this is, if you think of the anodes as electron pumps, and if you think of a flashlight as being an electron pump, which it is basically, if you turn a flashlight on or a torch and you hold it very close to the wall, you'll see one very, very bright spot. Then if you step away a little bit, you'll see a bit more that's reasonably bright. Then if you step back a bit further, you'll see a bit more, which is bright enough. A little bit further, and you maybe still see some, but you get to a point where you can't see the wall because you're too far away. So there's an optimum position for that torch or flashlight where you can see the maximum amount of wall with enough light that suits you. And that pretty much represents how we place the impressed current anodes, because we can just calculate how far away we need to be from the pipe in order to get a good distribution of the current. With galvanic anodes, however, it's a different kettle of fish, because they don't have a big driving voltage. And depending on the soil conditions and the pipe conditions, you might need quite a lot of them. And that's rather analogous to, say, being in a big cathedral with no lights but candles. And if you light one candle, you don't see very much. But if 100 people light candles and stand around the walls, you'll see the whole place illuminated just from the candles. And that's pretty much how we place the galvanic anodes. We do a calculation to show how far it will stretch and how it will deliver the current over its entire design life till it gets down to just about 20% of it being left. And we can then say, okay, on that basis, we need one every 50 meters, every 100 meters, every 10 meters, whatever it happens to be, depending on the conditions. The CP design is where the cathodic protection expert comes into his own, really. It's the professional close attention to design issues, leaving no stone unturned in order to produce a decent design. And you'll notice here I've captured the classical 3 engineers. That's one to read, one to write, and one to look after the 2 clever ones. So basically, there's an awful lot of guesswork in CP design because we have to try and guess what the performance of the coating is going to be like over the time. We have to guess whether or not the operation of the pipeline is going to change, whether there's going to be a new railway coming along, whether there's going to be overhead power lines, buried power lines, and all kinds of things. So the cathodic protection design is usually quite conservative. And of course, somebody somewhere sometime has to do the maths, and this has to be checked by a qualified CP specialist, in this case, a Frenchman. Now, how do we assess whether or not CP is effective? And the way we do it is we take a measurement of the voltage of the pipe. And the way we do that is at the above ground test posts, we connect a voltmeter to the test post and we stick a probe in the ground. And we use a special kind of probe because you want to be sure that sticking the probe in the ground isn't affecting the circuit you're measuring. So we use a thing on shore for a thing called copper sulfate reference electrode is the reference we use. And this, if it's kept clean and properly maintained, will allow you to make repeat measurements in a consistent manner. And it just so happens that the copper sulfate reference electrode will give you a negative voltage. And in this case, it doesn't mean that negative is bad. We give recommendations in the various standards of having a potential between minus 0.85 volts and minus 1.2 volts with respect to a copper sulfate reference electrode. But these aren't really criteria in the way that you might want them in other fields of engineering and science, because it varies so much on other considerations, where you actually place the electrode, how you place the electrode, what kind of instruments you use, what's the soil resistivity like, is there any electrical interference? So, but those are the general voltages that we like to stick around. Now, I've thrown in a few pictures to try and put some sense and proportion to it. On the left, you can see a ground bed trench, and they've excavated the ground bed. The engineer will have designed the length and the diameter of the ground bed he needs. And then we put in some carbonaceous backfill, some coke usually, coke breeze. And the reason for doing that is it provides a uniform and consistent low resistance connection for the anodes, which you can see on the right, to make contact with the soil. And you can see there the guy's been measuring the distance between the anodes because we will have calculated how far apart they need to be to operate without interfering with each other. Because one of the I should have mentioned there are two laws really, not just Ohm's law. Ohm's law is very important, but the one that trumps Ohm's law every time is Sod's law or Murphy's law. And that tells you that if you put these anodes too close together, they interfere with each other and reduce the total output. So we have to calculate how far apart we need them. And then the red cables here, they sit on this little shelf, and then the backfill would be filled over the top of those. And these cables would then run to a test post, so you could connect them to your power supply, and the power supply would be connected to the pipe as well. This is an above ground test post, and here you can see where the cables are coming into terminals inside, and they would be connected and distributed to other areas. This is a power supply, a typical DC power supply. This one here is remotely controlled, so you can adjust the output of it remotely, and you can make it vary its output automatically depending on what signal values it gets back from the pipe and the electrodes. And it's you can see that one's at 1.47, and it's got things like a lightning suppressor, an auxiliary power supply, which is now forbidden. You're not allowed to use those. And this is the actual DC generating part of it. It's called a switch mode power supply, and that's the remote control system that monitors and controls it. This is a similar switch mode power supply, but without the remote monitoring. That one's connected to a SCADA system. Here's a small solar powered system on a gas pipeline. Because modern coatings are so good, if you choose the right coatings or the right tapes, quality of them these days is so good that you get very few coating defects, especially if the job is watched as this thing goes in the ditch and they don't fill it with rocks and so on. But you need very little current, so you actually can protect them with small systems. This is the inside of a solar power data logging system. So now we know that the pipeline is judged to be protected if the potential stays within those fairly narrow limits of minus 0.85 and minus 1.2 volts. Bear in mind, the more negative it goes, the more cathodic protection there is. So we know from Faraday's law that if you have 1 amp DC leaving a carbon steel pipe in soil, it will consume approximately 9.1 kilos of steel. And that's not an option, it's Faraday's law. Now, luckily, we're not usually dealing with currents at that level when we just put the pipe in the ground. It's only when we get external interference that we get currents in the ampere range as opposed into the microamps or milliamps if you're unlucky in the absence of those. So we're very concerned in cathodic protection about how much current we put on the pipe and how much current is going to be coming off the pipe. And for this reason, we have what we call potentiostatic transformer rectifiers, where you say to it, I don't care what current you need, put enough current on that pipe to make sure the potential always stays between minus 0.85 and minus 1.2. And it will change its output automatically to maintain the static potential that you've given it. But DC stray currents are a major problem for us now in pipelines because, well, it's always been well known, but it's becoming more prevalent now because of the energy corridors we use, where land, particularly in this country, where land is not so abundant, we don't have a lot of real estate, so they tend to put the pipes and the overhead power lines in the same corridor. And we now have these, electrically speaking, horrendous wind farms generating high DC voltages, which have a massive effect on, can have a massive effect on pipelines, especially as the way they operate the wind farms varies depending on what they're feeling like when they had their breakfast or which direction they wanted to go. Some of them change direction completely. They have, for example, between Sweden and Finland, they have an exchange system where there's demand in Finland, they send current from Sweden. When there's a demand in Sweden, they send current from Finland. So the poor old CP guy doesn't know whether he's Arthur or Martha by the time he's finished trying to work out what the potentials are doing, because he's got a little black book that says minus 0.85 to minus 1.2. And you can see the currents going up and down with enormous excursions outside those limits. And the question is, does it matter? How do we deal with it? And we have written in the new standard some guidelines about how to deal with those rapidly varying values. But you shouldn't lose sight of the fact that even on the London Underground, which we do a lot of work on, you can draw several thousand amperes if you get two trains coming into a certain station at the same time, one from the up direction, one from the down direction. And if the station's on the top of a slight hill, which some of them are, and the trains need extra current to get up that little hill, and if it happens to be full of commuters, you can be pulling several thousand amperes easily. And it's not strictly true, but from the point of view of an understanding and practicality, it's reasonably correct to say that the metal loss is more or less linear. If you have 1 amp DC for 1 year, and you have 1 amp for a day, and you have 1 amp for a second, or you have 1,000 amp for 20 seconds, you can work out by simple linear relationships how much metal you're using. And the sources of straight current are increasing. We've always had AC and DC railways. We've got tram systems now, trolley bus systems, welding operations in factories and shipyards, especially if they're lazy and they don't place their return connections for the welding in a sensible place. Metro systems, tidal effects, the movement of the tides can induce voltages on pipes. Industrial solar power systems cause interference to pipes. Wind farms are a menace because they very often generate DC, and they transport that to somewhere where they chop up the DC to make AC. When you do that, you create all kinds of harmonics and electrical interference. You get high voltage DC cables above ground and buried. You get adjacent CP systems. And believe it or not, pipelines can be affected by space weather events. Magnetic storms, telluric currents, they induce voltages in buried pipelines, and there's not much you can do about it. You can't go and turn the sun off. So this concern did actually make it onto the government's risk register, and we did a little bit of work on that. And for those who like to be punished, I could send them a copy of a paper that I presented in Barcelona a year ago on how to calculate the effect of telluric currents. But unless you're heavily into maths, it's a bit heavy going. AC straight current is also a nuisance. Firstly, it behaves differently to DC, and the calculations that you need to estimate the corrosion risk are quite complicated. You can do them by hand, if you've got simple math software like MATLAB or MathCAD, you can do them. But here's the very easy way to understand this. There's a whole day's worth of paper in this anyway, but there's an easy way to understand it. If you look at the little electromagnetic wave, the first thing to remember is you cannot have an electric current without generating an electric and magnetic field. Not possible. They can't exist on their own. So you've got a magnetic field which is varying in a sinusoidal manner, which is what your 50 cycles per second is in the UK. That waveform there is called sinusoidal, as is that one. But you can see that the magnetic field is at right angles to the direction of travel, whereas the electric field is perpendicular, it's vertical. That's why the calculations become so difficult, because the angle at which these things interfere with the buried steel dictates very much how much voltage is induced. And there's nothing you can do about this, because these overhead power lines carry very high voltages and currents, and they generate big fields, and they're changing 50 times a second. And there's nothing, absolutely nothing you can do about it. And if it happens to be feeding a factory, particularly one, say, with welding or with equipment that changes the electrical phase, you'll find that the third harmonics all add up. So what starts off as a relatively small voltage gets bigger because the third harmonics are in sequence and they add up to each other. So that is what causes the problem. And what we have to do is we have to work out the impedance of the pipeline, the distance from each of the different wires in the overhead power line, and what the relation of those wires is to each other, because that affects the phases. And once you've worked out the impedance, which is same as resistance in many respects, then you can work out how much voltage gets induced in the pipe. Again, there's a lot of detail in the new standard that we've written. So I think I've pretty much covered what's on this slide in the last discussion, but it's just good to remember that the greater the magnetic field and the faster it changes, the greater the induced voltage. And some of these overhead power lines are big voltages. 600,000 volts is not unusual. This incidentally also gives rise to unacceptable touch potentials. So if you've got some poor chump who touches the pipe and then puts his other hand on a valve that's not electrically isolated, you can get a severe shock, and we have to take care of that too. So in summary, we can say that the corrosion of the pipe is associated with current leaving the pipe, and that CP is about putting current onto the pipe for whatever reason. Metal consumption is directly proportional to the magnitude of the current. And here's where the issue comes again with the coatings, because when I first started in coatings, there wasn't the wide variety or the high quality coatings available that there are now. And we only had two specifications, really. It had to be black, it was asphalt. And if it was really corrosive, it was thick and black. And that was all there was to it. There was no lovely three-layer polyethylenes, no lovely butylene tapes or anything like that. And what's happened now is that, in the old days rather, I should say, that when the coating failed, it fell off in big chunks. So the current density was quite low because your corrosion was spread over a big area, and therefore you got away with it. But these days, the coatings are so good that you just get a small nick, say 1 centimeter square. All of your corrosion takes place there. All of your 9.1 kilos per amp per year takes place in this 1 centimeter square. And that's why these stray currents are such a worry, because it can be like a hot knife going through butter. Right. Although I've made light of the principles, the scientific principles and the maths behind cathodic protection in an effort to explain it to you so you have a feeling for it, I haven't covered them in this presentation because they're just a bit overwhelming and frankly, unless you're a specialist in the field, not terribly interesting to you. But there are some additional resources. Now, Pig also did a very nice presentation by Chris Atkins, and that's also on the Pig YouTube channel. And I consider that this presentation is the primer, really, for that presentation. So if you have a little interest to go further, then you could very well benefit from watching Chris's YouTube video. That was a very good introduction. And if you want to take it any further, then there is the NACE. It used to be the National Association of Corrosion Engineers, which everybody understood, but now it's no longer the National Association of Corrosion Engineers, it's called NACE. And the UK Institute of Corrosion, they have some training systems that you might want to take part in. So Thank you very much. It's been a bit of a long presentation, but sometimes it takes longer to explain things than it does to actually just show the maths. But I hope it's been a bit of some interest to you and inspired you to be kinder to the CP engineer. You can probably see on the photo around my part on the participants is me with a flak jacket on. That is not to protect myself from project managers. We were just doing a job in a war zone. So you don't need a flak jacket necessarily if you're involved in CP. So again, thanks to Dr. Loeffler from Decotec for his technical contributions on the modern coatings. And I understand that they are actually going to make a presentation on the modern tapes and the benefits that they bring on a separate date. But any questions, please don't hesitate to contact either myself by email or Richard Lindley, or even via the Guild. And if you're not a member of the Guild, you should seriously think about joining, because there are many great benefits. Now I can see that we've got a few calls, so I'm just going to mute my mic for a moment and have a look at the chats and see if I can answer those questions, but keep them coming.
Thank you very much for your presentation, Ken. It was very interesting and very informative. Apologies, I think we have overrun a little bit, and the suggestion from presentation organizer is to send all the questions to Ken, and they'll be all answered later on at a later stage. So thank you very much, everybody, for dialing in. Please look out for the other pipeline industry Guild's future presentations and webinars. They are both being organized by various branches. A couple of few that are coming, they are next week. One is next Thursday, on the 16th of July, and it is pipeline rehabilitation, structural PE, semi-structural PE, and spray liners. And the second one is on Friday, next Friday, 17th of July, and it is HU pipeline quiz. So as Ken mentioned, please send your questions into the chat box. I've got lots of questions already there. We'll all send them to Ken, and Ken will respond to those questions after, and it will be distributed to everyone along with the presentation. Thank you very much, everyone.
I didn't know we had such a tight time scale. Do we not have any time to answer any questions now, Kate?
No, sorry, we were due to finish 15 minutes ago. So yeah, people are saying that they've got to go to other meetings and what have you. So I think it's best if we will download all of the questions and then we will send it across to you, and then you can answer them from there.
Okay, and what happens to them from there, Kate? Do you then distribute to all the people who joined?
Yeah, like you did before, we'll put it onto the format that you used before, and then I will send it out to everybody that's registered for today, and they'll get sent out to everybody.
Thank you. Well, congratulations to all of those of you who survived through to the end.